Okay, so here we are now on part 4 of exam 3. And in this, we are going to apply the von Neumann stability analysis to number 2 and show the requirement for stability. So I just started off with having what we found in number 2 written out. This was our final thing. That's n plus 1. Sorry, that looks so bad. And then we also have our r to keep in mind that we came up with last time. So we need to keep in mind that that n and j are increments for time and for length. And in our corresponding, in correspondence, t can be used as our time, whereas x can be used for position length. So we know that t is equal to n times delta t, and then we also know that x is equal to j delta x. Okay, so now I'm going to bring back the t and j equation that we found in number 1, or that was used in number 1. So we have t with respect to n and j, and as we remember, that was equal to e negative alpha k squared. Let's redo that. K squared, sorry about that, times t. And then that was multiplied by our e to the ikx. So now what we are going to do is we are going to plug in our t and x here for t right there and x right there. So it then equals e to the negative, and obviously we still have our alpha, still have our excuse me, just moved into a new house and one of the roommates has a cat, so I think I'm in the same boat as you and have allergies. So instead of our t, we have our n delta t, and then it is multiplied by e to the I k. Now instead of x, we have j delta x. Sorry if my j's look uppercase. My name is Josh, obviously, you'll see from the YouTube channel. And I'm just so, I don't know why, I've never really written undercase j's. I'm just so used to writing j's like this. I don't even put the top hat or whatever on. I just keep it like this. All right, so just wanted to mention that. All right, now moving on. Next thing we know is that e jx is equal to lovely sines and cosine. So it is cosine of x, and that is then multiplied by j. I'll try sometimes, but I don't get upset if I forget. Cosine xj sine of x. So now we can set our tn plus 1 here equal to what we just found here. So we will have t n plus 1, and then we have our j, and that is equal to our t and j, and that is being added to our t and j multiplied by our r, and then in our parentheses we are going to have e to the ik delta x and then that is being subtracted from 2, which is then being added to e to the negative j k delta x. Redo that. Delta x. So now what we can do is we can plug in the ejx. Obviously we got that right here, and then we'll plug it in to this equation so that we can get a little bit of a new one. So that's going to now turn into t of n plus 1 j, and basically this right here, that'll stay the same. This is the variable that we have, isn't in this or affects it in any way. But now obviously stuff inside the parentheses are going to be a little bit different. So we start off by having cosine of delta x, I'm sorry, k delta x, can't forget the k, and then this is going to be multiplied by our j sine of k delta x, big I there, oh goodness, terrible x. And then our 2 stays the same. That doesn't get changed by anything. We're still subtracting from 2. But then finally, we are adding now cosine of k delta x. And then now we are subtracting j sine of k delta x. Close off the parentheses there. Alright, so now we can go ahead and cancel out our j sines of delta x, since, I mean, they cancel out. So that now leaves us with t n plus 1 j, and that's still going to be equal to the stuff that we have on the outside. That doesn't change from canceling out the signs. So we'll have time n division j plus r t n j, and that is now multiplied by a pretty simple version. So obviously we have one cosine k delta x and another cosine k delta x, so that just becomes 2. So we have 1 plus 2 cosine, I'm sorry, no, let me redo that real quick. Just getting a teeny bit ahead of myself. We have 2 cosine k delta x, and that is being subtracted from the 2. Alright, so now this simplifies down a teeny bit more. So we still have our t and j plus r times t and j, and now the cosine, or now this inside cosine part becomes 1 plus 2 cosine, and this is just we're just basically completing the square here, just so we can have a simpler form for later when we are analyzing it. All right, so now, so if the value that we found is greater than 1, it leads to instability, and that is not what we want to do. So we need to keep it negative, or I'm sorry, we need to keep it less than 1 by setting up a couple parameters. So our parameters are here. We have the absolute value of 1 plus 2r cosine of k to the delta x minus 1. And like I said, that has to be less than 1 or else it'll be unstable. So we can do a little bit of maneuvering with this, and then we'll get negative 1 is less than, and then on the inside, what's this called? Absolute value goes away. That's what we're doing in this step. We get 1 plus r2 r cosine of k delta x and that is still being subtracted from 1, but now we also have r greater than 1, or I'm sorry, less than 1. So finally, we can have it as negative 2. Just getting rid of these ones here, and then we'll have, or I'm sorry, getting rid of this one, and then we'll have is a little less than 2r cosine of k delta x minus 1, but now we have less than 0, which is good. So the smallest value that could exist that we have that we found with this is negative 2. So this means that negative 2 is less than 2r times negative 2. We do a little bit of rearranging with that, some multiplication, division, flipping of the sign because of negatives, and we get that r is less than 1/2. So for our value for r, it needs to be less than 1/2 so that our system is stable. So that wraps up part 4, and I will see you in part 5.